This lecture video is all about exponential functions, including their graphs. An exponential function is any function that can be written in the form f of x equals b to the x, where the base b is greater than 0, but not equal to 1. Notice that if b were equal to 1, this would just be 1 to the x, and f of x would be equivalent to the constant function f of x equals 1. Let's practice this new idea by first evaluating an exponential function. In example 1, we have f of x equals 3 times 2 to the x minus 4 plus 29. We're going to find f of 10. F of 10 is the value we get when we substitute 10 for x in this function. So we have 3 times 2 to the 10 minus 4 plus 29. It's really important that we use good order of operations when simplifying this expression. We need to first simplify the exponent. 10 minus 4 is 6, so this is 3 times 2 to the 6th plus 29. And 2 to the 6th is 64, so we have 3 times 64 plus 29. Next, in our order of operations, we need to multiply. 3 times 64 is 192, so we have 192 plus 29, or 221. Let's take a look at what graphs of exponential functions look like. Our goal here is to generalize the shape of the function f of x equals b to the x, for any value of b greater than 0. Let's start, however, with a value of b that is greater than 1. We will also start with a specific example. Let's begin with b equal to 2. So our exponential function is f of x equals 2 to the x, and we'll make a table of values. For our x values, let's use integers from -3 to +3. If x is equal to -3, then f of x is 2 raised to the exponent of -3. 2 to the -3 is equivalent to 1 over 2 cubed, or 1 over 8. When x is equal to -2, f of x is 2 raised to the exponent of -2. 2 to the -2 is equivalent to 1 over 2 squared, or 1/4. When x is equal to -1, f of x is 2 raised to the exponent of -1, or 1 over 2 to the first, which is 1/2. When x is equal to 0, f of x is equal to 2 to the 0 power, or 1. And when x is equal to 1, we have 2 to the first, which is 2. When x is equal to 2, we have 2 squared, or 4. And when x is equal to 3, we have 2 cubed, which is 8. This gives us a list of 7 ordered pairs that we can plot on our xy coordinate system. Our first set of coordinates is -3, 1, 8. So we'll go to the left 3 units and up 1, 8. When x was -2, we found a y value of 1/4, so we'll move to the left 2 units and up 1/4. When x is equal to -1, we have a y value of 1/2, so we'll move to the left 1 unit and up 1/2. When x is 0, y is 1. So we have the y-intercept, 0, 1. When x is 1, y is 2. So we move to the right 1 and up 2. When x is 2, y is 4. So we'll move to the right 2 and up 4. And finally, when x is 3, y is 8. So we'll move to the right 3 and up 8. Notice the trends that we see with these coordinate points. The smaller the x value gets, the tinier our fraction will be, and it will never actually reach 0. That is, on this graph, as we move to the left, our points will approach the x-axis. With positive x values, our y values get larger and larger very quickly and head off to infinity. When the graph of a function approaches a horizontal line as it moves to the left or the right, this is called a horizontal asymptote. We draw it as a dashed line because the points on this line are not actually part of our graph. They will get closer and closer to it, but they will never quite reach it. For this graph, our horizontal asymptote is the horizontal line y equals 0. Also notice that we have a domain of all real numbers because the exponent can take on any value, negative, positive, or 0. And we can tell from the graph that the range of this function is all positive numbers, that is, from 0 to infinity, not including 0. Let's generalize what we've just found for any value of b greater than 1. If we are graphing the function f of x equals b to the x, where b is greater than 1, there are some very specific points that we will be able to easily graph. Consider when x is equal to -1. Then we will have b raised to the power of -1, which is 1 over b. When x is equal to 0, f of x is b to the 0, or 1. And when x is equal to +1, we have b raised to the first power, or simply b. Those are the points -1, 1 over b, 0, 1, and 1b. Notice that all exponential functions of this form will have the same y-intercept, because any number raised to the exponent of 0 is equal to 1. Let's take a look at an example. Here in example 2, we're going to graph the exponential function 4 to the x. The first thing that we'll do is draw in the horizontal asymptote, which is the x-axis, or the horizontal line y equals 0. Next, we'll plot those three specific points when x is equal to -1, 0, and 1. First, let's consider the y-intercept. When x is equal to 0, y is always going to be 1, because any number raised to the 0 power is equal to 1. And with our base of 4, we will also have the point 1, 4. When x is 1, y is equal to the base, in this case 4. And the point -1, 1/4, because when x is equal to -1, the y value is 1/4. Let's plot these 3 points, 0, 1, 1, 4, and -1, 1/4. Third, we'll draw in our smooth curve, being sure not to cross the horizontal asymptote. Finally, let's make note of the domain and range. The graph goes forever to the left and to the right, so the domain is -infinity to +infinity. And the range is 0 to infinity, not including 0. Because looking up and down, we notice that we approach 0 as the graph comes down, and we approach infinity as the graph goes up. Now let's consider values for b that are between 0 and 1. We already considered the case where b is greater than 1, but now let's look at values for b that are less than 1 but still positive. For an example, let's look at f of x equals 1/2 raised to the power of x. Let's consider the same x values that we did when our base was 2. When x is equal to -3, we have 1/2 raised to the exponent of -3. This is equivalent to the reciprocal of 1/2 cubed, or simply 2 cubed, or 8. When x is equal to -2, we have 1/2 raised to the exponent of -2. And finding the reciprocal of 1/2, we have 2 squared, or 4. When x is equal to -1, we have 1/2 raised to the exponent of -1. That's the reciprocal of 1/2, or 2 to the first, which is 2. When x is equal to 0, we have 1/2 raised to the power of 0, which is 1. And when x is 1, we have 1/2 raised to the first power, which is 1/2. When x is equal to 2, we have 1/2 squared, which is 1/4. And when x is 3, we have 1/2 cubed, or 1 over 8. Let's plot these 7 points. We first have the point -3, +8, then -2, 4. Next we have -1, 2, and 0, 1. When x is 1, y is 1/2. When x is 2, y is 1/4. When x is 3, y is 1/8. And we continue approaching 0 as we head to the right. Connecting these dots with a smooth curve, we have a slightly different looking exponential function. But there are also a lot of similarities. We still have a horizontal asymptote of y equals 0. We also still have a y-intercept of 0, 1. And the other 2 points that we noted before are also the same. When x is equal to -1, y is still equal to the reciprocal of b, which in this case is the reciprocal of 1/2, or 2. And when x is equal to 1, we still have a y value of b, which in this case was 1/2. We can still use the same 3 points to help us sketch the exponential functions even when the base is less than 1. Let's try out an example. Let's graph the function f of x equals 1/4 to the x. We will follow the same process. We'll start by plotting the horizontal asymptote, which is still the x-axis, or the line y equals 0, and we'll plot those same 3 points. when x is equal to -1, 0, and +1. All graphs of this form have the y-intercept of 0, 1. That is, when x is 0, y is equal to 1. When x is 1, y is simply b. In this case, our base is 1/4, so we have the point 1, 1/4. And when x is -1, y is the reciprocal of the base. And with our base being 1/4, we have the point -1, 4, because the reciprocal of 1/4 is 4/1. Now we'll connect these points with a smooth curve. Now we have the graph of 1/4 raised to the exponent of x. To finish this, we'll note the domain and range. The domain is all possible x values, and looking left and right, we can go forever to the left and right. That is, the domain is -infinity to +infinity. Also notice that that means that our exponent can be negatives, 0, or positives. The range is 0 to infinity. As we go down, our graph still approaches 0, but never reaches it. And as we go up, the graph goes on forever, so we go to infinity. Now let's consider a very special base. Similar to the irrational number pi that is very useful in many applications, the natural base is denoted e, and it's approximately equal to 2.718. This is a number that we will often use as the base of an exponential function. It's also referred to as the banker's constant because it's used when we calculate compound interest. You might notice that your calculator has a built-in e button, much like it has a built-in pi button. It's often associated with the ln button and possibly right above it. The natural exponential function is the function f of x equals e to the power of x. Let's practice with this natural base by evaluating the natural exponential function at 2 and -3. f of 2 is equal to e raised to the exponent of 2. This is the exact answer, but for an approximation, we use our calculators and raise e to the power of 2. And rounding to the nearest thousandth, we get 7.389. f of -3 is e raised to the exponent of -3, which is also the same as 1/e cubed. That's our exact answer, but we can approximate this using our calculators. And rounding to the nearest thousand, we have 0.050. We can also graph this function similarly to how we graphed our previous exponential functions. Since e is greater than 1, we can use the generalizations that we found for a base greater than 1, such as a horizontal asymptote of y equal to 0. Let's make a quick table of values to plot some points. For the x values, let's use integers from -2 to +2, because e to the third won't fit on our graph anyway. When x is equal to -2, f of x is equal to e raised to the exponent of -2, or 1/e squared. To help us graph this, we'll use the approximation of 0.14. When x is equal to -1, f of x is e raised to the exponent of -1, or 1/e, which is approximately equal to 0.37. When x is equal to 0, we have e raised to the 0 power, or simply 1. When x is 1, we have e raised to the first power, or e, which is approximately equal to 2.72. When x is 2, f of x is e squared, which is approximately equal to 7.39. Let's plot these 5 points. We have -2.14, -1.37, 0, 1, 1, 2.72, and 2, 7.39. And with these points, we can construct our graph. Those points give us a really good idea of the shape of e to the x. Notice that we still have a y-intercept at 0, 1. We also have the point 1e and the point -1, 1/e. We also have a domain of -infinity to +infinity and a range of 0 to infinity, not including 0. Now that we're familiar with exponential functions, let's take a look at some exponential equations and learn how to solve them. An exponential equation is an equation containing a variable in an exponent. And we have a really useful property called the one-to-one property of exponential functions. Consider a base b that's a positive real number that's not 1, and real numbers r and s. If b to the r is equal to b to the s, then we have that r is equal to s. In other words, exponents are unique. There are not two different exponents that we can raise a base to and get the same number. They must be the same exponent. To help understand this rule, let's take a look at example 5. First, we have 4 to the x equals 256. The first thing we want to do is write 256 as a power of 4. 256 is 4 to the 4th, so we can rewrite this equation as 4 to the x equals 4 to the 4th. Now we have the same base raised to two exponents, so those two exponents must be equal. That is, x is equal to 4. Now let's look at 2 raised to the exponent of 3x minus 2 equals 128. Since our base on the left side is 2, our first step is going to be to write 228 as a power of 2. 128 is 2 to the 7th, so we can rewrite this equation as 2 to the 3x minus 2 equals 2 to the 7th. Now we have the same base, 2, raised to two exponents. So those two exponents must equal one another. That is, 3x minus 2 equals 7. Solving for x, we'll add 2 to both sides, giving us 3x equals 9. And dividing both sides by 3, we find that x is equal to 3. So our solution to this equation is 3. That concludes this lecture video on exponential functions. We looked at their graphs and solved some exponential equations.